On this example, we're given a graph and we're trying to come up with an equation that's going to give us this graph. So in looking at this, it's kind of a strange looking graph. I know that it's either going to be a secant or it's going to be a cosecant graph. And we kind of have to make a decision which one we want to utilize. We can use either one. I'll show you how to set this up and find either for secant or for cosecant. But I'm going to choose the easiest direction the first way through, and then a little bit more difficult to show you how the other one goes. It's really not that difficult. This throws students off a lot, just picking the right one to begin with. So let's remember that secant is associated with the cosine graph, and then cosecant is associated with the sine graph. So when we're thinking about this, let's first kind of graph these and get the basic shape. I'll show you how to do this. So if we graph the sine graph, I think most students are pretty comfortable with what that looks like, something along these lines. Now, wherever you end up with having a 0 for the cosine graph, that's what's graphed in blue, whenever it has an x-intercept, you end up with a vertical asymptote to go along with the secant graph. And then remember how this kind of works is you're inverting, you're flipping upside down using the reciprocals of each one of these y values. So it matches up here at the top, but as you approach that vertical asymptote, it's going to go up there. You kind of get this loop at the bottom where this point matches up, and it goes down. And the other one here, those points match up and you go up. It's kind of what's in orange there. That's going to be the secant graph. Next, let's take a look at the cosecant graph by first looking at sine. So sine starts at the origin, goes up, comes down, ends up at the origin. Again, wherever you have an x-intercept here, you're going to get a vertical asymptote for the cosecant graph. So it looks like we get 3 going along there. And then this time, you meet up, that point's in common for both these graphs, but it goes up with these loops. And then on this side, kind of come down, or come up, and then go back down. So the orange graph there corresponds with our cosecant graph, just the basic shape of it. So let's look at the graph that we're actually given. It looks to me like we have a vertical asymptote going on at the y-axis, another one here at 2, and finally another one here at 4. I'm just going to focus on those because it looks like we've completed one period. If we want to think of it as being the cosecant graph, remember it had vertical asymptote at the y-axis as well, and then 2 more before it kind of started repeating itself and its period completed. So for our example, I'm first going to think about this as being the cosecant graph. So I'm going to go y equals a times the cosecant of b times x, and I'll put a plus d out here at the end. Why I'm not including c in this case is because c would represent a horizontal shift, but this one seems to start at the y-axis, right, being where our vertical asymptote is, so it hasn't been shifted over. We will need that horizontal shift when we use the secant function in a second. All right, so I'll show you how each one of these steps works. All right, the first thing I'm going to go find is, let's think about a. All right, a is basically, it's the middle. All right, so if you can pick out half the distance between the lowest value here and the highest value over here, half that distance is going to be whatever a is. All right, so basically you do a subtraction here if you wanted to, or looking at our graph, we have like 3 units above the x-axis. It looks like 5 units below the x-axis before we get to that loop at the bottom. So that's 8 total, but we want to take half of that, so we do 8 divided by 2 is going to be 4 for our value for a. Okay, not too bad. You could call this a midline if we were dealing with either the sine or cosine graph. Shouldn't be too bad. It's right in the middle, basically, right? Or it would be the amplitude, I guess, for sine or cosine. All right, so we know 4, so let's kind of fill that in. We have y equals 4 times, remember we're using the cosecant of bx plus d. Okay, next let's think about b. b has something to do with the period. All right, this is going to affect the period. Now our normal cosecant graph begins at 0, ends at 2 pi, so we'd say it has a period of 2 pi. Our graph, a little bit different, right? It's not 2 pi for our period. It looks like it starts at the y-axis for one period, and it ends at this next, the third vertical asymptote that I've drawn in there. So that begins at 0 and ends at 4. So the period here is 4 for our graph. Now how that connects together with B is we always take the original period, for cosecant, and divide it by whatever B is. So in our case, the original period for cosecant is going to be 2 pi, and then we divide that by B. Well, now we have an equation because that has to equal 4, the period of this graph. We should be able to solve for B. So to do so, I'm going to go ahead and multiply both sides by B. Can't really solve for it while it's in the denominator. That'll leave us 2 pi on the right-hand side, 4b on the left-hand side as I've written it. And to get b all by itself, we need to divide both sides by 4. All right, so this will put b on the left-hand side all by itself. And then a little bit of reducing down on the right-hand side, we can say this is pi over 2. So as we continue to fill in and build this up, we now have y equals 4 cosecant of pi over 2x plus d. Okay, d happens to be what you would consider maybe the midline. If it was sine or cosine, basically what you want to do is figure out what line, horizontal line, would go directly in the middle of our graph. So it's kind of like the average between that lowest value we get to here at 3, and then the highest value we get to here at -5. So basically take that average. So d is going to be the average there. We go 3 plus -5. And then since you're taking an average, you have two values. You're going to divide that by 2. So we get -2 over 2 is -1. So d is -1. We get y equals 4 cosecant of pi over 2x. Then a -1 or a plus a -1 at the end. So that would be one solution that would give us that graph. Now, if you needed to do it using the secant graph, what that would mean is you would want to entail basically starting right here and then completing the period right here, like one time through. Hopefully that makes sense, that connects with the secant graph, that you have a loop going up, you got a loop at the bottom, and then you finish here at the bottom again. All right, so it has the exact same period. It has the exact same kind of bottom of the loops, top of the loops is going on. So everything's the exact same as what we just found for the cosecant as far as A, B, and D goes. The only thing that's different is normally our secant graph begins at the y-axis, but it looks like this one's been shifted to the right 1 unit. All right, so how we can account for that, going down here, is we can say, well, we have y equals 4 secant of pi over 2, but then on the inside here, we're going to do an x minus c. And then at the end, I guess we still have that d was the exact same value, so we'll do a -1. So c is going to be a horizontal shift. All right, in our case, because everything got moved to the right 1 unit, what we're going to do is use c equals +1. All right, so final answer on this, we're going to go y equals 4 times secant of pi over 2. And then inside here, we get x minus 1. And then that -1 at the very end for the vertical shift down. All right, so this is an alternate solution that you can use if you were asked to use secant or cosecant. Either one of those is the correct answer that would give us this exact same graph that was graphed at the beginning. And it does make sense that because we're moving to the right 1 unit, we're subtracting 1 directly from x. Hope this helps out. Good luck as you're working on going from graphs to functions.